Hey, pressure time. Got the weight of the world on us. And yep, there it is. Weight of the world. Oh, and I'm hitting the wrong button. Here it is. Here's the weight of the world. What is it? It's 1 atmosphere of pressure. Yeah. And that's basically, like we said, everywhere you go out here in the air under 1 atmosphere of pressure. What we want to calculate today or figure out today is how to find out how to calculate with a nice physics formula the pressure of water, pressure produced by water going down under the surface of the water. Okay, we start out with 1 atmosphere right here, and then as soon as we go down, it quickly goes up, right? Boom, 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 goes down. And what does the pressure depend on? Well, it depends on the weight of the water above us here. So it has to support all the water above us, plus the weight of the atmosphere, right? We could even take the atmosphere away. Boom. Turn it off because we're in a simulator. So we could do that. So there's no atmosphere, there's no pressure right here because there's no atmosphere to squeeze us. Pressure is actually a squeeze coming all around. As we go down, that pressure goes up quite rapidly as we go down into the water. And it's okay, what does it depend on? What does the pressure depend on here? If I'm at this one depth here, it's like about a meter underwater along this line. What's It's always the same on that line, right? 0.09 atmospheres on that line. So on this line, 0.09 atmospheres or 0.12 atmospheres on this line, 1.4, 1.7, and it's the same way all the way along the line. What about if we swim under the tunnel? Say we swim under the tunnel. Okay, well, I got to be under the tunnel. So if I swim under the tunnel, oh, I still am at this. If I'm at the same level, I still feel the same pressure. So what's going on? Somehow, the because the water molecules are all swimming around, banging into each other, they distribute that squeeze, that pressure squeeze, equally everywhere so that it only depends on your depth underwater, right? And then let's say now we have the atmosphere. So let's say we turn that back on because that's what real life is like. So we got 1 atmosphere of pressure. Notice to everywhere as we go down, what is added to it? 1 atmosphere of pressure, right? So that 1 atmosphere of pressure squeeze on the top of this fluid surface gets transmitted to everywhere in the fluid. And still, the pressure dependency only varies with depth in the fluid. So we want to figure out what that pressure dependency is so we can calculate it and not just use this gauge to find it. Oh my goodness. So let's see how we could do that. Let's go to this other simulator. Go to this other simulator and see if that's going to help us here. I'll grab that on my screen. Let's go. Okay, so let's see if we can figure out how to do that. Let's reset this thing. We'll reset all, but I'll go to buoyancy and I'll pick my block. Now my block is a cube, as you can see here. Well, we're just going to assume it's a cube actually, and I think we can see that it looks like it is. So let's assume it's a cube. Now when we take our cube here, and notice this cube has it's 0.4 times the density of water. Right? Water has a density of 1 kilogram per liter. We talked about that in the class before. 1 liter is 1,000 cubic centimeters, and the density of water is 1 gram per centimeter. So naturally, you're going to have 1 kilogram or 1,000 grams in 1,000 cubic centimeters, which equals 1 liter of water. But here, this has 40% of that, right? 0.4. So that's probably going to float, right? Yeah, we'll throw it in there. You see it floats. Interestingly, it displaces 2 liters of water. Interestingly, it displaces its weight in water. Okay, we're going to find out that that's Archimedes' principle. That's always true. but whatever. We don't want to talk about that now. What do we want to find out now? I want to know what is the pressure of the water that's holding this up. And it's got to be the pressure coming from the bottom, right? Because yeah, the water is exerting pressure on it everywhere, all the way around, from side to side. It's squeezing this way and squeezing this way on the sides, but those are just canceling each other out, right? The squeeze to the right is equal to the squeeze to the left. And of course, so that yeah, there's force balance. It's in force equilibrium because it's not moving. Now, is there pressure forces pushing it down? Yeah, there's actually atmospheric pressure pushing it down here on top. Is there pressures pushing it up? Absolutely. There's water pressure pushing up all along the face of the bottom. All right, and I want to know what that pressure is. So to know, and if it's pressure versus depth H for depth, I would need to know the depth from here to here. Okay, and maybe I could guess what it is, but they don't have a tape measure for me or anything like that, so I don't actually know just off the top of my head what that depth is. I know that this cube has it's the same length on every side, so I can actually figure out what the length of a side is, right? Because I know the cube is 5 liters. And since every side has the same length, each of those lengths would be the cube root of 5 liters, right? This is a vol because 5 liters is a volume. You take the cube root of it and you'll get the length. Okay, so fine. So I can figure that out. But meanwhile, I still don't know what the depth underwater of it is. Okay. Let's see how can we remedy this situation? What I would like to have this thing do is just sink under the water until it was just barely submerged, right? Let's see how I could work out to do that. I think if I make it heavier, I think that's going to work, right? Say I make it 4 kilograms. Blurp, 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 blurp. Yep, right? It got heavier. It got more dense. Yeah, because I kept it the same volume but increased the mass. So it now went to 80% of water, and we could say, whoa, it's kind of like looks like 80% submerged, but whatever. So what do you think? I'm thinking, what if we do this? Just make that 5. Blip, 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 blip. Yeah, okay, notice that it sinks down. This now, look, it has the same density as water, our block does. So if I just take it and just let it go from there, or just be very careful, just let it dip down from the top, right? Notice it's completely submerged, and it's the top of the cube is just kissing the water. And notice anywhere I put the block in the water, it just sits there. Which if you think about it for a second, that's the only thing it could do because it has the same density of water, so the water around it has to be treating it just as if it was other water. And what does the water do around other water? It just holds it up. So it sits there and doesn't move around, right? Because there's not a river, it's not flowing or anything. It's just if you were in this pool, you wouldn't feel any water splashing around unless you made that happen. Yeah, so it's just sitting in place. So the water just holds all the other water in place. So, okay, great. If I just sit it right there, now I know what this depth is. It's the height h of this cube. Okay, great. And then now can I figure out the pressure um, at the depth underwater? Yes, we can. We can figure out the pressure now because we know the mass of the cube and we know the depth of the cube. So we can figure out what the pressure must be, keeping it held up in the water there. Okay, let's get this figured out so we can get to the end of this video. Ho ho! Gotta click it. Click, click, click. Okay. All right. I gotta bring this up on my screen. Okay. So here we go. So here's the problem statement. Okay, so we know pressure is force per area. We want to know what is the pressure at the depth h beneath the water surface. and we know that that depth here is just the length of a face of the length of one of the sides of the cube, and we know it's a 5 kilogram cube. Find h at the same time. Okay, yeah. So, well, anyway, the upshot of this, if we recall, just go back to this. Is it this screen? No, this screen. The volume of the cube is 5 liters. So how could I figure out what h is knowing that? How to get that? Get my pen. Still select all. Okay. Now it's going to work. GIMP can be a challenge sometimes. But anyway, okay, so we know the volume here. What's that? That's equal to 5 liters, and that's equal to h cubed. Okay, and 5 liters, I could take the cube root of everything here and get h, and it'll be cube root of h. So h would be equal to cube root of 5 cube root of liters. So the units of the length would be cube root of liters. So that's not a measurement of length that I'm used to. So what could we do to that? Well, we know a liter is 1,000 cubic centimeters. So let's do it that way. So we'd have 5 times 10 to the 3 centimeters cubed. And now if we take the cube root of this thing, then we're going to get h is equal to the cube root of, okay, 5, and it will also be times the cube root of 10 cubed, which is just 10. Cube root of 5 times 10 centimeters. And I worked that out. That's equal to about 22, let's call it 0.4, 22.4 centimeters, rounded. Okay, or h is equal to 0.224 meters. So that's our depth underwater here in this case, just as a side note. Now we want to figure out what is the pressure that's holding it up. Okay, so let's consider the pressure on our cube here. And by the way, the cube has an area, the face has an area A, yeah, where that A is going to equal to what? H squared, right? Because the volume is h cubed, and the area of a face is h squared. So we'll just point that out because we can notice that pressure is equal to force divided by area. That's going to be important for us to know. So what do we got up here? So up on the top of the cube, right up here, remember it's just kissing the surface of the water. So pushing down all on the top of it is what? Atmospheric pressure right here, P0. This guy, 1 atmosphere of pressure is pushing down all on the face. Now on the sides, yeah, there's pressure on the sides, and there's pressure on this side, and we got pressure there, and the pressure going, here to the right is canceling the pressure to the left, quite obviously. What about on the bottom? Yeah, we got pressure all on the bottom, pushing it up. P, all that pressure P, and that's the pressure at a depth H, right? That's pushing this cube up. So how are we going to figure out what this is? Well, one way we could do it is go ahead and use force balance, right? This cube is just sitting there still, not moving in the water. That means the sum of the forces on it in every direction has to be 0. Okay, so side to side 0. We're not going to worry about that. Right, that's pretty much clear that's happening. Up and down, the forces also have to add to 0. So what are the forces going up? Well, the force going up is remember, pressure is equal to force times the area. So the force associated with the pressure, just move the area over to the left there, and then you'd have it. The force is equal to pressure times area. So here the area, just FYI, is h squared. So pushing up is the P at depth h times the area. That's the force pushing up. What are the forces down on the cube? Well, it's the weight of the cube, mg. So it's 5 kilograms times gravity going down. Also going down is the atmospheric pressure right here, P0. P0 times A is pushing down at it. Okay, so for force balance, what do we have to have? We have to have the sum of the forces in every direction equals 0, or forces up equal forces down. So we could just we could set the forces up equal forces down right here. That means P times A is equal to mg plus P0 times A. mg plus P0 times A. All right, well, let's see. If we know what P0 is, and we know what A is, we know what M is, we know what G, right, is 9.8 meters per second squared. We could actually calculate it right now, but actually we're looking for something a little more general than that. We want a formula that just is for general, what is the pressure in a fluid going down, where we have quantities that are related to the fluid itself. And let's remember that the density of our block right here, the density of our block is naturally defined as the mass of the block over the volume of the block. That's equal to the density of water here, of rho, let's call it rho water, which we'll also just call rho. So that means that, we just come over here, that the mass of our block could also be written as the density times the volume. And the volume of our block is, not h squared, it's h cubed. H cubed. Holy cow. Okay, got that sorted out. All right, so this equation has to be true. Squirrel that off for ourselves. Okay, so that's great. Now, what I'm going to want to do is substitute in this for my mass over here. Okay, and A. So I'm going to substitute that in for the mass. Well, let's go in steps here. So let's just take this equation and come over here. Let's block all this stuff off. Get this equation. So let's show you. We have P times A is equal to, I'll just go in steps here. Now I have mass. Instead, I'm going to write it as rho times volume, okay, times G, rho volume G, plus P0 A. Now, what we'll do in the next step is substitute in, since we have A's and we have V's, but those are both can be written in terms of the H's, we'll substitute those H's in now. So this one is PH squared is equal to rho times, I'll put G over here, just move the volume and the G, and this is H cubed now for the volume, plus P0 H squared. Here we can see now we have a common term of H in each of these. I can cancel through by H squared. What is that going to give me? That's going to give me P, okay, just dividing through by H squared is equal to rho G H plus P0. And this, friends, is what we wanted all along. That is our formula for pressure going down in a fluid, right? Because remember, this density rho from our calculation was equal to rho of the water, or the density of the fluid. So you're saying that the pressure underwater is equal to the density of the fluid times gravity times the depth h underwater plus whatever part is squeezing down at the top, P0, that's 1 atmosphere, typically. Whatever it is, whatever's up there. And for us, here on the Earth, kicking around, that will be 1 atmosphere of pressure. All right, let's stop the video right there. And I'll catch you on the next video.